Hi there, so this video is going to be a nice 2-for-1 video, and so we're going to prove that this equation 1 over x is a hyperbola. Now it's also on this other side here as well, but I don't really care. I'm dumb. I'm too dumb for having both sides. And I mean, once we understand this one side, we get the other. Anyway, so this is a hyperbola, but it's not your normal hyperbola equation, right? Normally, it's going to be, the general form is, let's say, something like this. So we're translating x here, squared over, well, let's call it x naught, right? This is going to be the equation of a hyperbola over something. We'll just call it a squared. And we can have over here y minus y naught. So translating y squared over some number, we'll just call it b squared, equals something. Maybe call it c squared. I don't know. Actually, yeah. I think usually it just equals 1, but you know, in general. And there's something with these a's and b's and some kind of formula with that that's interesting, but that's not what this is about. But anyway, there's a general form of a hyperbola, and this is not it. And yet, people are saying generally that this is a hyperbola. And this 1 over x equation comes up a lot because it's just a reciprocal, basically. We're saying y equals 1 over x. So y is the reciprocal of x. So you have something and its reciprocal. And in some cases, you can consider this reciprocal to be a kind of an inverse in certain contexts. But I'll just call it a reciprocal, I suppose. So this happens quite a lot. Okay, it's everywhere. You can also think of like e to the x and e to the negative x. Those are also reciprocals. So they have this general relationship. I'll call it a hyperbolic relationship. So we want to prove that this is a hyperbola. And normally this is done through typically using a matrix or something that's going to simply rotate this by 45 degrees, and then you check and prove that it's a hyperbola. And those methods are out there. I'm gonna do something different, or at least it seems to be different at first. Later, we'll analyze it more carefully and figure out that we're doing the same thing as rotating by 45 degrees, really. But the way of thinking is different. And I said this video is a 2-for-1 because, so I'm going to show you the method, and I'm going to suggest it as an exercise because once I show you it, it's fairly straightforward. However, what I really secretly want to do is ramble about some deep mathematics, because I think this is connected to some very, very deep mathematics. In particular, I mean, this is a hyperbola, so we're in the realm of hyperbolic geometry, which is the realm of relativity, or special relativity in any case. So hyperbolic geometry, I mean, this is like the simplest, more or less the simplest sort of quintessential example of hyperbolic anything for me. So hyperbolic geometry is a much deeper, more general subject, but so this is sort of the first, or one of the first examples you want to look at. So anyway, so you're going to get a ramble from me about deeper math that I think is very interesting. But first I just want to say that what's the method I'm going to apply here? I'm going to define something as mu, and I'm going to, basically this is going to be the average. So we're going to take the average of x and y. So x is x, and y is 1 over x. So whatever we have, we take the average of it. Now this over 2 can be viewed as a scaling factor. So in more general contexts, we maybe don't care. The thing is that we're adding the two things. And I'm going to define sigma as something very similar, but we subtract. We could subtract the other way. How things pan out is going to end up being the same thing. more or less. I mean, it's a good exercise to think about what if you did the subtraction the other way. It's good. So I'm going to... So here's mu and here's sigma. I've just defined these things. Sigma is kind of like the average, but it's more focused on some kind of difference. So whatever this is, whatever. Okay, I've defined these things. Well, you can, as an exercise, do mu squared, and let's subtract sigma squared and see what you get. And if you do that, you'll see that you get something that looks like a hyperbola, the equation of a hyperbola. And so for me, this kind of proves that it's a hyperbola, but I'll maybe return to this. What I want to talk about, again, this is a 2-for-1, is rambling about this pattern. And I think it's a very general, important pattern for higher mathematics, deeper mathematics. It's a simple pattern. I want to tell a little bit the story of why I started focusing on this and thinking about it a lot. Now, spoiler, it's really just whatever graph you have, it's really just rotating it by 45 degrees. If you graph then mu and sigma, basically, my sigmas always look a little weird. Sigma. Whatever we had for y and x, say that we had the graph was going up here, that is where the average is increasing, but sigma is not increasing. So that is like increasing mu, but not increasing sigma. Whereas if I go, say, this way, okay, it's a little confusing to look at. But I think, so here I will be, so this is x minus y will be increasing, but the average will not be increasing. So maybe not the best explanation, but it's left as an exercise to you to really analyze this and figure it out, see what's happening in general, and unless I've made some terrible mistake, I'm pretty sure you're going to find that this mu sigma graph is really just rotating by 45 degrees, and there's a scaling factor, this 2 here. So we can get rid of the 2's, or I think you need to do root 2 if you want no scaling. Anyway, I'm not too concerned about the scaling factor because it's not particularly complicated. And if you choose sigma, if you choose the subtraction the other way, it should rotate in the opposite direction. So spoiler, what we're really doing is just rotating and scaling a bit, and you might say, well, it's not very interesting. Okay, and fair enough. But a couple of questions. One, is there maybe... but what's interesting to me is, for one thing, this sort of creates a new vector space, that if you could even have just, well, 2 parameters on a one-dimensional space, that's basically, because you have 2 parameters, or 2 degrees of freedom, now it's a 2-dimensional space, so you're kind of cheating. But anyway, you have 2 parameters, you can always take the mu sigma, or you have some kind of space, you can always look at these mu sigmas, and it just creates a new vector space. And I mean, that's kind of interesting, but it's kind of not interesting because you're really, again, just rotating things. And you can ask, well, what if I do the mu sigma transformation again, a second time? You're just going back to the x and y graph. So, again, maybe doesn't seem to be too interesting. But at some point, somewhere in deeper maths, the world of Lie algebras and Jordan algebras and this kind of stuff, is there something interesting here? Is this part of a bigger pattern of valuable mathematics? And is there maybe something algebraic that happens at some point? Is there something we can do with this? And I don't entirely know, but I think that what I do want to say, I just want to talk about this pattern because you see it in many situations. If, for example, you look at the definition of hyperbolic cosine and sine, if you're not familiar, there's such a thing as hyperbolic trigonometry. So it goes along with hyperbolic, or sorry, it goes along with, yeah, hyperbolic geometry and that kind of stuff. So there's kind of the Euler form of this, which is going to be this over 2. And this one is going to be very similar, but with a minus. This was kind of part of my initial inspiration for looking at this mu sigma thing. It's this general pattern. If you want to do just cosine, not the hyperbolic version, but the circular version, the ordinary trigonometry stuff, you need to put i's here, and here, and an I here. And then you get the Euler form for cosine and sine. Very interesting stuff. Again, as an exercise, you can practice. Take these and do mu sigma of this, and you'll get, I think you'll, I can't remember for the cosine and sine, but if you do it for cos and sinh, the hyperbolic versions, you should just get ex and e to the negative x. Maybe you get it also with this. I need to do that as an exercise. Good exercise, just kind of fun. I'm just going to reverse this. And so it's, you can see this pattern, this sort of mu sigma pattern alive and well here. There's a couple more places where I want to say that it pops up. And one is in the world of Lie algebras and Jordan algebras. I think it pops up. But first, actually, let's get out of the way, because this is a bit complicated. Let's get out of the way a simpler example, which I finally found. It's sort of silly that I didn't know it until a few months ago. But if you're gonna, you can take a matrix and decompose it into symmetric and asymmetric components. So let's say A is a matrix. Okay, just gonna put that here so people can, so it's very clear. A is a matrix, and so I can break it apart into symmetric and asymmetric parts. And the way I do that is using the transpose. And so I'll take A plus the transpose of the matrix and take the average of those. And I'll take A and minus the transpose. And again, you can do transpose minus A. I don't think it'll make a difference. It's a difference of signs. You can work it out. But let's prove that this is equal to A. Well, the denominators are the same, so we just get, we'll get 2A on top, and just basic algebra, we'll get minus 2. Am I doing this right? Sorry. We'll get plus A transpose and minus A transpose on top, all over 2, which this will cancel, and we get A. So this is always true. And what's happened here is that this is now a symmetric matrix, and this is an asymmetric matrix. Asymmetric matrix. So yeah, so matrices can be decomposed into symmetric and asymmetric versions, and that's actually super interesting and super useful in my opinion. But it's, do you see, it's the exact same pattern. So this pattern that I thought was really important, and sort of universally, generally important. I'm like, this mu sigma thing, this mu sigma transformation, more people need to be talking about this. This is like part of an important general pattern. That's what I was thinking. And then for a year or two, I've been thinking about that. And, you know, not every waking moment, but sometimes. And then a few months ago, I was looking up how to decompose a matrix into symmetric and asymmetric parts, because I seem to recall that you could do that. And it was this formula, and I'm like, oh, that's exactly the thing. So it seems to be a pattern of decomposing something into its symmetric and asymmetric parts. And somehow this is basically, there's some kind of correspondence here between the concept of even and odd in functions. And I haven't really thought about this, so maybe somebody who's watching could think about this and explain in the comments what the correspondence is between this sort of mu sigma thing, or and or this sort of symmetric, asymmetric thing, and the concept of even and odd functions, there's some kind of correspondence there, and it might be obvious, but I just haven't spent the time to really think about it. But I think it might be important as well. Okay, and then there's the mess of, well, I shouldn't say mess, but there's the whole business of Lie algebras and Jordan algebras. And so Lie algebras are going to be asymmetric. You're going to have E to some matrix, and generally the matrix that you put in here, the trace is 0. So it doesn't have to be 0, 0. It could be like A minus A. But it's going to have something here and something here. So they're generally, I think they're all always asymmetric matrices. I could be wrong. But when you talk about a Lie algebra, to me, I'm immediately thinking something asymmetric. And it's basically more or less, Lie algebras are basically like the commutators from, or sorry, the Lie bracket. Lie algebras, for Lie algebra, you have to define a Lie bracket. Now, I'm not going to go into all the stuff of Lie algebras. It's a deep topic. But more or less, the Lie bracket is like a commutator, for if you've studied commutators in quantum mechanics. So it's reminiscent of the idea, or it's basically exactly the same as the idea of how you can have position and momentum in quantum mechanics, but you cannot simultaneously measure both. So, and then there's the business of Jordan algebras. And Jordan algebras, it's a topic that at times you might look at it and say, okay, that's simple. It's kind of like, it's like Lie algebras, but it's sort of like a symmetric, it's focused on symmetry rather than anti-symmetry. But there's some deep and weird and complicated things. It's kind of a deep subject and not super straightforward. And I have a couple books on the subject, but I don't really properly understand it. It's on my list of homework to study more. And however, generally speaking, there's sort of, it's kind of like what I said. Lie algebras are really about anti-symmetry. Jordan algebras are really about symmetry. And I think you can often combine them into Clifford algebras. If you have a Clifford algebra, I think you can generally decompose it into a Lie part and a Jordan part. Now, Clifford algebras are, let me write it out. Clifford algebras are associative, whereas octonionic algebras are not associative. Octonionic. So there are, I believe there should be Lie algebras that do not fit into the whole Clifford algebra, or this is AKA geometric algebra. I'll just write GA, geometric algebra, which there's a lot of interest on YouTube about geometric algebra. And so if you gave me a Clifford algebra, I'd be thinking, how can I decompose this into symmetric and anti-symmetric parts? That's basically, the symmetric part is going to be your dot product, and the anti-symmetric part is going to be kind of your spinners, but it's the, what do they call it? There's an inner product and the outer product. So there'll be an inner product, and the outer product is a wedge. It'll be the wedge project. So your wedge product is anti-symmetric. You can kind of think the wedge product is like the generalization of the cross product. Okay, so yeah, dot product symmetric, wedge product anti-symmetric. Okay, and however, there's something going on with the octonions and the exceptional Lie algebras that is different, that is not described in these Clifford algebras. There's something, because it's the octonionic algebra is or the octonion algebra, I guess I should say, it is not associative. Okay, so there's something weird going on. But there's a lot of study of this kind of stuff and how it relates to, well, there's basically an attempt at unification. It's a candidate for unification to make use of the octonions. And there's some very interesting stuff. You can look up, Colfuri talks about this. If you want to find, just search Colfuri octonions, or just searching octonions will probably get you what you're interested in. Specifically, somewhere in here, somewhere this guy, Latham Boyle, he has a YouTube channel. He was talking about Jordan algebras. I think it's this 14th talk here, but I'm not totally sure. There's a whole playlist. Hold on. There's a whole playlist here of lots of interesting stuff. I think, yeah, you have Colfuri. So RCHO, it's the real numbers, complex numbers, quaternions, and then the octonions. So yeah, like I said, it's a unification candidate for the unification of physics. John Bias has lots of interesting stuff to say about all this stuff. But I think it's this talk or something by this Latham Boyle guy, that's him, where he talks about Jordan algebras. And if I recall correctly, which my memory might be wrong, but there's this F4 symmetry. That's one of the exceptional Lie algebras. And there's something like with the Jordan algebras, you can, I think, get this F4 symmetry, and that it's basically equivalent to all the observables in quantum mechanics. I'm sort of paraphrasing, and my memory might be wrong here, but I think that's what he does in that talk, is he explains how you can use Jordan algebras to create F4 symmetry, and they can describe all the observables in quantum mechanics. So the kind of picture that I have here in my head is that when you have something anti-symmetric like position and momentum, then they can't be observed simultaneously. But these symmetric things, that somehow when we make, quote-unquote, make an observation, whatever that means, or take a measurement, quote-unquote, that we're getting the symmetric parts of whatever's happening. There's some kind of process happening. Symmetric. I mean, I'm talking about physics that we don't know yet, okay? I'm talking about unification physics. It's not established, right? There's some kind of process going on. Maybe it's knots of space-time or something. Who knows? But it has symmetric and anti-symmetric parts. And when we take a measurement, we're somehow getting, or we're having an effect on the system, okay? And we end up with this symmetric part of the process that you could say, I guess, the system sort of collapses to where we get this output that is just the symmetric part. Does that make sense? When we do a measurement, we do something to the system, and the output that we get is just the symmetric part. And the symmetric part is information that we get out, the measurement. So that's where you have there's basically a correspondence to what I'm saying with the idea that, the imaginary part of a wave function in quantum mechanics will sort of collapse or go away when you take a measurement. When we take a measurement, we get real values from a wave function. So, okay, so that's interesting. And anyway, there's some correspondence between these Lie algebras and Jordan algebras and the symmetric anti-symmetric pattern in general. Something very deep going on. And that was a ramble. That was a genuine ramble. But I think it's very interesting to think about. So now let's get back to this, and we need to prove that this is a hyperbola. So when I take mu squared here, I'm going to zoom in and make this thing a little bit thinner. So I take mu squared, I'm going to get on top, I'm going to get x squared plus 2 times x times 1 over x, so those are going to cancel, plus 1 over x squared. So mu squared okay, let's do this. Mu squared equals 1 over 4 times this, because the denominator will have a 1 over 4. Right? And so that becomes 1. So we get x squared plus 1 over x squared over 4. So that's an interesting thing, how this middle term canceled. And we'll do, gosh, I should make some space for myself. Hold on. Okay, let's do sigma squared. We're going to get x squared minus 2x 1 over x plus 1 over x squared, and it's all over 4. Okay, so equals x squared minus 2 plus 1 over x squared over 4. Now, what happens when I do mu squared minus sigma squared? Well, these terms are going to cancel. This x squared and 1 over x squared and the x squared 1 over x squared here are going to all cancel. And so we're going to get, but we're going to have this minus 2. So we're going to get, we have minus 2, so we get positive 2 over 4, which is 1/2. So mu squared minus sigma squared equals 1/2, which is the formula of a hyperbola. So that means when we take this, we do this mu sigma transformation, we get the equation of a hyperbola. And if you study this mu sigma transformation, you find out again that you're just rotating by 45 degrees. So to me, this is enough. Maybe I need a little more explanation or something, but this is enough to prove in my head that this has the same structure as a hyperbola. And that's it. So yeah, let me know what you think of that. I know it's a little... this stuff, it's not that hand-wavy to me, but if you think it's hand-wavy, maybe tell me what you need to better explain it. And the standard, this talk, pretty interesting. The triality stuff is very interesting and dear to my heart. I'll just talk about that briefly. Because if you study Lie groups and Lie algebras, I don't have any space anymore. Let's do this. Let's do that. Okay. So there we go. If you study Lie groups and Lie algebras, then you eventually learn that Dinkin diagrams are the way that the Lie algebras are classified, or at least the complex Lie algebras are classified using Dinkin diagrams. They're also sometimes called Dinkin-Coxeter diagrams. There's a small difference between Dinkin diagrams and Coxeter diagrams. It's mainly about... I won't get into it. Anyway, there's these Dinkin diagrams, and of particular importance, you have this D4 graph. Looks like... I'll just draw it. This is D4. And so the D4 graph is where you have this sort of a basic example of this triality thing. So if you want to learn about this, look up triality and Cartan. Let me just find it for you, because actually it might not be enough. So I believe, yeah, you actually want to find, well, it's in French. Le principe de dualité et la théorie des groupes simples et semi-simples is where Cartan talks about, Elie Cartan. He introduces this concept of triality. Now he calls it duality because the word triality didn't exist at the time. And there's some very interesting matrices. Let's go, where does he talk about them? Here's the matrices. So there's, I know it's very hard to see, but so you can find it on your own computer. We can zoom in here. How do I... these matrices. So you have H, this matrix right here, H. You have K. Now, if you square H, what happens is this bottom right 3 by 3 stays the same, but the negatives switch over here to being on the left side. It's a good exercise. You can, well, it's probably written right over here. H squared. There's H squared. So H and K, these matrices form the generators of a finite group of order 6. That's what he says right here. They form a finite group of order 6. And so you have, along with the identity matrix, you have these 5 matrices that you see right here, and then the identity matrix. And H and K are your generators of the finite group. And this is exhibiting sort of triality. I think it's like the group, is it just called S3? Basically, I think it's isomorphic, but... so this is sort of the beginning of the idea of triality, and inside of this Dinkin diagram, there's triality. And if you... So, other Dinkin diagrams, like, for example... So as soon as I do this, now, do you see that D4 is in here? So 1, 2, 3, 4, 5... Am I doing this right? 1, 2, 3, 4, 5, 6. Is this E6? Something wrong. I feel like there's something wrong. But anyway, as you draw E6, E7, E8 of the Dinkin diagrams, you still have this D4 inside. You still have this triality in there. So in the octonions, you have triality going on. And John Baez talks a lot about it, and he's got a good paper sort of introducing octonions. If you search octonions Baez, you'll find good stuff. But so I think that understanding this triality is kind of the key to understanding F4, E6, E7, E8. These are the, okay, there's also G2. G2, these are the 5 exceptional Lie groups, or 5 exceptional Lie algebras. And G2 just looks like it has 2 nodes, and but it has 3 things connecting it. And basically, you can get from here to here through what's called Dinkin diagram folding. So you can imagine just these, we collapse these nodes all together, and you end up with 3, what do you call them, edges. You have 3 edges connecting 2 nodes then. So through Dinkin diagram folding, we can go from D4 to G2, and G2 is the automorphism group of the octonions. So within octonion algebra, you have this G2 thing. Now, to go further, there's a process that is sort of weird and complicated to understand. And I'm kind of drawing a blank on how to explain it, but I think so. I'm a little bit confused on how to explain. I've understood this before, what I want to explain, but I can't remember. But anyway, when you go up from over here going this direction, you have the complexification of the octonions, which looks like this. And then you have the sort of the quaternionification or something like that. And then for E8, you have this direct product. But there's something weird going on. There's something very weird going on. But John Baez talks about this. And actually, I mean, Vladimir Arnold, I'll just abbreviate Arnold, great mathematician. And he's talked about, I saw a lecture from 1998 where he's talking about some stuff. And he says, you know, he's heard great mathematicians say this, what I just said, like the E6 is complexification and quaternionification and octonionification, blah, blah, blah. He says, great mathematicians have said this. And he said, this guy said it, and then this guy said it. So it must be true, but I do not understand it. So Vladimir Arnold, who's a great mathematician, said that in a talk in 1998. So don't worry too much. I feel like I've kind of understood it for brief moments, but but it comes to me a bit. I'd have to really dive into it again if I wanted to really explain this. But John Baez talks about it. Anyway, so from the Dinkin diagram D4, you can sort of collapse it through Dinkin diagram folding to get G2. And then this triality that's happening already with D4 is kind of the key. It's the complicated part of these more complicated diagrams. So 1, 2, 3, 4, 5, 6, 7, 8. I think this is E8, if I drew it correctly. And that's the most complicated exceptional Lie algebra. And you've got this D4 right here, which is giving you the triality, and that's like the really complicated part of understanding this stuff. So my advice is, if you want to understand Dinkin diagrams and the classification of Lie algebras and try to make some kind of intuitive sense of these more complicated Lie groups and all that, focus on triality and really try to understand D4 and then build up from there. So that's my little advice, and I think that's enough for today. This is quite complicated stuff that I do not myself understand very well. Hope you enjoyed it. Leave a comment. Let me know what you thought. Bye. Thank you.